Wednesday, my dudes. Something like that. Anyway, day 145. Here we go. So, frequency and period and wavelength and solving problems involving those things. Um, and so, those are the goals, right? That you memorize the relationship between frequency and period, that you realize that when the frequency, when the waves come by more often, that the length of each wave, the time period for each wave is shorter. Uh, and it's a squirrel, and vice versa when the time period for one wave is bigger, right? When a wave is wider and moving slower, that they come less frequently, they come less often. So let's get into it. So that's the relationship between frequency and period right there. I gave it away. If you haven't done the rest of the warm up yet, please do so right now. Attempt it and pause this video and then unpause when you come back. Okay. So we're looking at this problem. It gives us amplitude, frequency, and distance from crest to trough. We have to find the period. As we discussed the other day, amplitude doesn't affect the period. Amplitude affects the amount of energy something has, right? A taller wave has more energy. These guys are having a lot of fun. A taller wave has more energy. Think about getting hit by a taller wave at the beach, or think of a tidal wave, right? They're immensely tall. But it doesn't affect the period or anything else. So we just need the frequency and the wavelength. Is this the wavelength then? Distance from crest to trough. Let's look at a picture. So here's a wave. All right, and one wave would be from this green dot here all the way till we get back to the same spot there. Okay, not here, but over there. And so a whole wave cycle. One up, one down, and then back. Ooh, we missed that. One up, one down, and then back to where we started. So if we go from crest to trough, we're going from here, the crest or the peak, to the trough, the lowest point. Is that a whole wave cycle? No. How much is it? Well, if the whole thing is from here to there, or another way of saying the whole thing is from peak or crest to the next crest, and we just go from crest to trough, how much wave is that? It's half. So we need the whole thing. So we know that this half is 12.8 centimeters. So the whole thing must be double that. So if I was going to use my equation to find the period, how would I do that? Let's go find some equations. Where'd they go? Oops. Okay, sorry, computer difficulties. So we go and look for the wavelength, we know the amplitude, we know the frequency. We've got all this information, we got to find the period. So here's all the equations that we know right here. 1, 2, 3. And I want the period. What letter is the period? That one, T. So I see it in two places. I see it here in this velocity wavelength equation, and I see it here in this frequency period equation. With these two equations, I only know enough to solve one of these. Oh, these squirrels are really going for it. Okay, so I don't know the velocity, so I can't solve this problem. I could figure it out. I could plug in the wavelength and the frequency, figure out the velocity, put that here, and solve for the period. But the easier way to go is just to use this one because I already know frequency. So I have to rearrange this equation. The way you rearrange it, you would solve for period, for t. Basically, that just involves these two things, frequency and period, trading places. So the new equation would be period equals 1 over frequency. And so I just have to divide by the frequency, and that'll get me the period. Seems simple. The frequency was 51.2 hertz. That means that 51.2 waves go by in a second. That's a lot of waves. It's like, all right, really fast. Probably a little bit faster than what I just made with my tongue. All right, so 1 divided by 51.8 is a period of 0.019, all this business. So I get 3 sig figs for this problem, so it's going to be this. 0.00193. That's it. That's the whole problem. Okay, for the rest of the day, you're going to be doing some practice problems. First, I want you to watch a video, then do a little reading, and then solve some problems. The problems are meant to be really short and quick. Like I'm saying right here, 30 to 90 seconds for each one. So that's half a minute to a minute and a half. These problems down here, half a minute to 2 minutes each. So the whole thing, you should be able to do it in about 50 minutes. We got a quiz coming Friday just to assess where you are and see how you're doing. So that I can make some plans for next week. So beware for that. It's going to be vocab. It's going to be math problems like this. It's going to be like finding things like where would you measure the wavelength to and from, like we just talked about earlier, right? If I give you from crest to trough, and then say find the wavelength, you need to be able to go, oh, that's half a wave. Just multiply it by 2. To get the whole wave. Okay, so videos. We got a video from the science classroom. So let me open this up. And this is great. It's only about 3.5 minutes. Big plus for this video. He goes through how to solve 3 different kinds of problems. One with wave speed, one with frequency, one with wavelength. And shows all the steps. So that's really nice if you still want some help with learning how to solve these problems. Pretty sure this is an ad. All right. Sweet. Doopity doop. So all about using the wave equation. He goes over the parts, talks about waves and what one wavelength is, and then you get to solve this problem, right? Speed, wavelength, period. Great stuff. And he explains all the steps. Super. Okay. Then you've got some practice problems. So physics classroom, talking about what frequency is, what the hertz is, what period, what it means to be periodic. So these are all key things to understand. This is the equations that we were just talking about. And here are the practice problems. So you can try them out. You can click to see what the answers are. Talks about why the answer is what it is. So everything is there for you for those. And in the second part for today, we've got wave speed. Great video from Bozeman Science. He starts it off really cool with talking about lightning. Lightning is a wave that you see, right? It's the light. But then you also hear thunder, right? Lightning and the thunder. I was going to sing the song, but it's too corny. So you see both, right? And they travel at different speeds. So it's a great way of thinking about wave speed that we experience in our daily life. And he's going to use, to talk about speed, something that all great science teachers use. This, right? The FET wave simulator tool, waves on a string. This thing's great. So he's going to talk about this and how to measure stuff. And if you had a hard time with the lab and you're still working on it, he'll give you some tips with that right here. Some things you can pick up. But that's those. And then the practice problems, it's the same thing. Some good reading about speed and like different media and how waves travel at different speeds through different materials. We talk about tension. Um, you might think of pulling on a rope, but when we're talking about a material, right, like water or air, you're hearing me through water or air right now. Air. Is there like a string of air, like a rope in between the speaker on your computer or on your phone and your ear? Well, no. So how could there be some kind of pulling tension? Well, all particles are bonded together, right? They're connected, um, and there's some kind of attraction between each one, and so that's the tension that we're talking about. For air, it's not a whole lot of tension. I can do all of this. I'm sure that can turn into a meme, right? Great, good job, me. But if I had, say, a piece of metal, you can't move it like that. There's more tension there, right? And my ring, right, there's more tension there, and so sound travels a lot faster through metal. Something that's kind of in between those two things, water. You may have learned that whales and other animals can communicate via sounds that they make in the water for miles and miles. That sound travels a lot better in the water. Also travels a lot faster because it's more dense. The particles are more densely packed, more tightly packed, and there's more tension there. So we'll talk about wave speed, um, and and then there's some practice problems down here. Okay. So any questions about those? Let me know. Again, the answers are all here. So this is really good practice stuff, and that's it from me. Have a great day. Do something nice for yourself. Um, be good.